MDM4U 8.6 confidence intervals. We're going to recall some previous concepts that will be helpful to our understanding of confidence intervals. Standard deviation measures the dispersion of data in the population to the mean. So if we can recall that parameters measure some aspect of the population, meaning each and every single item in that could be selected, mu, or for a population proportion, p. And what we do in statistics is take a sample to get a statistic, either x bar, which is a sample mean, or we're trying to find out in that sample what proportion has a certain characteristics, and we use the symbol p hat to approximate that statistic. So that statistic is approximating that parameter, and what we're going to be talking about is the standard error. It's a measure of the dispersion of a sample statistic around the population parameter based on a sample size n. So if we were to take a sample from the population, and we're going to talk about the parameter mu, we're trying to estimate that, and if we were to take a sample from the population, this one right here has 1, 2, 3, 4, 5, 6, we would expect that there'd be some dispersion of our actual sample mean around the population mean, mu. Because a small sample would likely to have some fluctuation. And we talked about the kurtosis of our distribution of sample means. If we have a larger sample, we would expect that it would be the sample mean would be closer to the population mean. And what we can do is use the sample mean, so the mean of the sample means, as an approximation for the population mean. And based on the size of our sample, that would affect the distribution of these sample means. So you can see in this formula that if you take the population standard deviation and divide it by the square root of n, you will get the standard deviation of the sample means. And we call this the standard error. Similarly, the standard error for a proportion, we can use the mean of the sample proportions, p hat, as an approximation for the proportion of the population. If we took multiple repeated samples of the same size, we would get some to be above, some below. It would be distributed around the actual population proportion. With a standard error, so the distribution of the sample proportions would be given by the equation square root of pq over n. And remember that q is just 1 minus p. Probability of success p, probability of failure q. So, as we mentioned that the sample mean can approximate the population mean, it'll be distributed around that population mean. If we were to get a specific result in a sample, how confident can we be that it is close to the actual population mean? And what we can do is establish a certain width to which that population mean belongs. So above and below our sample mean, we would expect to see there's a certain width that we could expect to see our population mean reside. So let's talk about confidence intervals. A confidence interval is a range of values that is centered on the sample mean and has a specified probability of including the population mean, mu. Example, there is a 0.9 probability that mu will lie between the upper and lower limits of 90% confidence interval. So, the confidence level is the probability that a measurement or conclusion is correct. The confidence level is equal to 1 minus alpha, where alpha is the significance level. So, with a confidence interval, what we're doing is centering an interval around the observation, the sample mean, and taking steps to the right and left based on that sample mean to try to estimate where the true population mean would be located. So what we're doing is using z-scores based on a sampling distribution to take a certain number of steps so that we have within, with the center around our mean, our sampling mean, we're going to take a step so that if we want a 95% confidence level, for example, that would mean that there's 5% significance level. And we're going to have that significance level on the two tails. So 95% confidence level, 5% significance level. We will split that into the two tails, 2.5%. So what we need is the z-score of a normal distribution to determine how far away is that from the mean in terms of standard deviations. So in this chart here, you can see that if we have a tail size of 0.025, that's half of 5, we need a z-score of 1.960. And I'll just illustrate that here. Negative 1.96 has a probability of 2.5 to the left. And we'll just investigate another one. 90% would mean that on each tail, on the left-hand side and on the right-hand side, we would have 5% on each. So when do we see approximately 5% of the area to the left of our z-score value? We're getting close here and here. Between these two values is 0.05. So a good estimate is to take the midpoint between negative 1.6, 0, 1, 2, 3, 4, and 5. So between 4 and 5, we end up with the following value. Between negative 1.64 and negative 1.65 is this value here. Add them together, divide by 2. So that's the z-score value, which will have this much area to the left-hand side, the alpha over 2 z-score value. So when we're talking about the mean, we can use the following interval to estimate the population mean. So notice that we're using x bar plus and minus a certain value to come up with that interval. We're using our observations in a sample and then using the z-score times the standard error for a random variable, for the standard error for the sampling distribution, to approximate how far that width needs to be to get a specific level of confidence. So a paint manufacturer knows that the standard deviation, sigma, for the drying time is 10.5 minutes. A sample of 20 equally sized areas had a sample mean x bar of 75.4 minutes. Find a 95% confidence level for the actual mean drying time of the paint. So let's look at our given information. We were given the standard deviation is 10.5 minutes, and that was given from the population. Our sample observation was 75.4 minutes, and this was for 20 equally sized areas, and the significance level is 5 if we have a confidence level of 95%. It's the complement. So we substitute into our formula, and this tells us that we have 95% of the time our population will be between, or we can be 95% confident that the population mean is between these two values based on our sample observations. So let's try to do the exact same thing for a proportion. So voter turnout in municipal elections is often low. In a recent election, the mayor got 53% of the votes, but only 1,500 voters turned out. So construct a 90% confidence interval for the proportion of people who support the mayor. Now notice that this is similar. We're estimating a population parameter for the proportion from a population as a certain characteristic by using p hat. You see how it's p hat plus and p hat minus as the center for our interval. And then we'll use the z-score times the standard error for a distribution of sample proportions to take a step to the left and take a step to the right to create that interval width. Now, we want to have a 90% confidence interval. That means that alpha is equal to 10%, n is equal to 1,500. If p, which is being approximated by our observation, our p hat, our sample proportion, is 53%, then the q hat, or the sample proportion of failure is 0.47. That's 1 minus this value. Substituting into our formula, we end up with an interval for 0.51 to 0.55 for our population parameter P, and we can be 90% confident that it falls between these two values. So, in the last example, we were basing everything on the confidence level that we wanted, but another way that you might want to create an interval is based on a desired width. So, that being said, given a sample of size n from a normal population with standard deviation sigma, you can use the sample mean to construct a confidence interval. You can express this confidence interval in terms of its central value and width. For example, suppose a sample of bolts has a 95% confidence interval of 7.51 millimeters for mu up to 7.55 millimeters for the diameters. You can express this interval as 95% confident estimate of 7.53 millimeters plus or minus 0.02 millimeters for the diameter of mu. Sometimes, however, a statistician might first decide on the confidence interval or width or margin of error. So it's the width of that confidence interval required, and then use this value to calculate the minimum sample size necessary to achieve this width. Opinion polls and other surveys are constructed this way. The width of a confidence interval, x bar, that's the center, plus or minus, this operator means we both add in one case and then subtract this value, the z-score for the tail size and the standard error. And we can simplify this to use this formula. In order to have a desired width, we would have to have a sample size n. So that's 2 times. Sample size for quality control testing. Suppose the diameters of the bolts mentioned above have a standard deviation of sigma is equal to 0.1. How large would a sample need to be for 90% confident that the diameter is 7.53 millimeters plus or minus 0.01 millimeters? So for a 90% confidence interval, that would mean that each of the tail sizes is 5%, and if we look on our chart, that is a z-score of 1.645. So 1.645 to the left and to the right to create those tail sizes of 5% on each tail. Substituting the known values into the equation gives the following. So n is equal to approximately 271. So you would need a sample size of about 270 bolts. So notice this width. I just want to state this. If it's plus and minus 0.01, that width is double that because it goes to the left and to the right. So just be conscious of that. Next, for proportions, it's a similar process. The sample size required for surveys involving population proportions is given by the following. The margin of error for a proportion is given by this right here. That's 2 times each of those interval lengths to the left and right. And isolated for n, we get this right here. Simplified, it is given by this formula. So let's apply it in this context. Sample size for a poll. A recent survey indicated that 82% of secondary school students graduate within 5 years of entering grade 9. This result is considered accurate within plus or minus 3%, 19 times in 20. Estimate the sample size of this survey. So, plus or minus 3% is a width of 6. If we have 19 times out of 20, then our error is 1 out of 20, which is 5%. So that's our significance level, the confidence level of 95%. And our population proportion is being estimated by our sample proportion. 82% was our value, so the complement of that is 0.18. Substituting into our formula, we end up with approximately 630.